All right, so this was a question I got emailed. Specifically, based on the direction field, determine the behavior of y as t goes to infinity. If this behavior depends on the initial value of y at t equals 0, describe the dependency. So what this student sent me was beautiful. It was a picture of their work, which you can see all down here, and a picture of the problem, so I didn't even have to try and dig out my textbook to figure out what the problem was. Thank you for that. So what I can see from their work is there's the differential equation. They set it equal to 0 to find the equilibrium solution, which they then plotted here. They then found a couple of the slopes for various y values and plotted those slope lines, those tangent lines. And I agree, right, when y equals 3/2, it has an equilibrium solution where the slope is 0, so it's a horizontal line. So draw a direction field for the given equation. So now, based on the direction field, determine the behavior of y as t goes to infinity. So again, what is y? Y is a solution to this differential equation. So it is a function, right? It is a function whose graph we could and should be able to draw. So when we look at our direction field again, what you are seeing here are tangent lines to potential solutions. So if this behavior depends on the initial value of y at t equals 0, so here's our t-axis. The derivative does not depend on t at all. It only depends on y, which is why all of our tangent line slopes here are all the same across a y. So let's say I drew some of these pictures earlier. I'm going to move this red dot, and let's say y is 2, right, when t is 0. So if this behavior depends on the initial value of y. So let's say that I'm looking at the ordered pair 0, 2, right? When t is 0, y is 2. If I look at that point, I can see the tangent line. It's going down. So let's try to be, I don't know how to do that symmetrically with the video. Anyway, it's going down, right? So if I were to draw what my graph would look like right here, it's going down. If I were to pick another, how about y equals 3? When y equals 3, my slope is going to be -3. So I didn't do this, but if I draw, let me see if I can insert just a whole bunch of little tiny lines. Pictures, shapes, let me draw a little line. So here's what my graph probably looks like so far. Let's make this red. Let's make it super fat. Boom. All right, that's my function so far. But as I kind of creep this way and this way, as I get up to where y equals 3 would be, well, now I know at y equals 3, my slope is -3. So at this point, my slope is actually steeper. Let's make this nice, fat, thick red line as well. Right, so really, if I'm kind of beginning to piece my picture together, and then if I go up even higher, y at 5, that slope is -7. So that's even steeper. So again, my function is not going to be a whole bunch of lines, but what I hope you can see as I'm kind of drawing these little linearizations of my curve based on their tangent line slopes is this curve that's going down, right? And in fact, as I get closer to 3/2, that slope is still going to be negative, but it's going to become smaller and smaller and smaller and smaller. And what you're eventually going to see is, I'm going to make that even fatter, weight, thicker, right? This nice, what looks like a exponential curve going down, right? So if I start above my equilibrium equation, right, what we have very nicely here, when y is greater than 3/2, what do I mean by that? When t is 0 and y is greater than 3/2, or greater than 3/2, the slope is not positive, the slope is negative, right? My slope is negative here, which means that, unless they were, okay, so when y is greater than 3/2, nope, slope's negative, so swap those words. If I'm above the equilibrium equation, my slope at my initial point is negative, so I'm getting this exponential decay, and it's tending towards, as t goes to infinity, what is happening to my function y? It's approaching 3/2. It's approaching the equilibrium equation. Well, what if I start below, right? So what if I take this green dot? What if instead I start at 0, 0, right? Let's let t be 0 and y be 0. So if I'm looking now at 0, 0, we didn't draw in those slopes, right? But if it's 0, then my slope is 3. So again, I can draw little tiny tangent lines and kind of draw a linearization and keep on going and keep on going. And what eventually you will get to and what you will see is something like this, right? That nice green curve. Like right there, the slope is 3. Here, the slope's probably a little less, like 2. Here, the slope is 1. Here, the slope's even less. The slope's getting smaller and smaller. And so I am, again, asymptotically getting closer to 3/2. So for number 1, determine the behavior of y as t goes to infinity. Well, it doesn't matter if you start above or below. As t goes to infinity, any tangent line drawing, as you piece all your little tangent line slopes together to draw your curve of what a potential y solution is, those will all, y, no matter what y actually is, y will tend towards 3/2, towards the equilibrium equation, which is why this equilibrium solution is called stable. So to give it, right, a nice, this is from our, right, I went to here, Desmos slope field generator, and then I turned off the movable point because I don't like it. And there's your equilibrium equation. If you solve this differential equation using the methods in the textbook, because it's a separable differential equation, you can get the following general solution. So again, if I'm looking at 2 for my initial y value, 0 is t, right? If I look at this point, 0 is t, y is 2. When you put 0 in here, right, e to the 0 is 1, and you put 2 in here, so 2 is equal to c plus 3/2. That means c has to equal 1/2. And that's giving me this nice red curve right here. Likewise, if I then use 0, 0, if I plug 0 in here and 0 in here, well, then that means c had better equal what? Not 1/2, but c should equal, if this is 0 and that's 0, then 0 is equal to c plus 3/2, so c should equal negative 3/2. And then, aha, lo and behold, if I change the color to be consistent, yeah, there's lots of cool things you can do with Desmos. Done, right? That's going to give me this green curve, kind of like what we drew over here. Now, you don't have to solve the differential equation, and in fact, in this section, that's not the goal. The goal is to think about drawing possible solutions without having the explicit equation y. So drawing a whole bunch of little tiny tangent lines and connecting it into a curve. What happens to the curve y as t goes to infinity? That's what this is asking.